In 2012, astronomers announced that they had found a planet made of diamond. Not a planet with diamonds on it, not a planet with a diamond buried somewhere inside. A world where diamond was the bedrock, a layer of it thousands of kilometres thick, wrapped around an iron core with a crust of graphite on top. It was 41 light-years away, in the constellation Cancri, orbiting a star you can just about see with the naked eye on a clear night. And the story went everywhere: newspapers, magazines, and television. A planet worth more than every diamond ever pulled out of the Earth, sitting in plain sight of anyone who knew where to look. That planet is real. Its name is 55 Cancri E, and it is still there, still orbiting, exactly where they said it was. It just isn't made of diamond. Within a year, someone went back and checked the numbers, and the diamond began to fall apart. Within 4, the model of the planet's interior had been rewritten into something that looked, of all things, ordinary: an iron core, a rocky mantle, a world built more or less like our own. The most valuable planet ever discovered had quietly turned back into a rock. Except that isn't where this ends, because in the years since, we have pointed the most powerful telescope ever built at that same world, and what came back was not an ordinary rock at all. It was something nobody had predicted, that by every rule we know should not be possible, and that our instruments still cannot agree on from one look to the next. So this is a story about a single question, asked over 14 years, that keeps refusing to stay answered. What is this planet actually made of? To understand how anyone could get this so wrong, you have to understand what we can and can't actually see. At 41 light-years, 55 Cancri E is not a disk in a telescope, it is not even a dot. We have never seen this planet. We have only ever seen its effects. When it passes in front of its star, the starlight dips by a fraction of a percent, and from the size of that dip, we get its width. From the tiny wobble it induces in the star, we get its mass. Put those two together, and you get the one number that starts every argument about a distant world. It's density. And density is a clue, but it's a maddeningly blunt one. Think of holding 2 identical sealed boxes, one in each hand. One is heavier, that tells you something real, but it doesn't tell you whether it's full of sand or water or lead shot or a single dense brick with air around it. Many different recipes give you the same weight. That's the position astronomers were in. 55 Cancri E is about 8 or 9 times the mass of Earth and about twice as wide, denser than water, less dense than pure iron. A rocky world, but which kind of rocky world? So you do the only other thing available. You look at the star. Planets and their stars condense out of the same cloud of gas and dust at the same time from the same material. So the star's recipe is a reasonable first guess at the planet's recipe, the way you might guess what a loaf of bread is made of by looking at what's left in the mixing bowl. And in 2010, when astronomers measured the chemistry of the star 55 Cancri, they got a number that changed everything. They found it had more carbon in it than oxygen. That sounds like a small technical detail. It is not. In planet building, the balance between carbon and oxygen is close to everything. Here's why. In our own solar system, oxygen is the more abundant of the two. There's roughly twice as much of it as carbon. And oxygen is greedy. As a young planetary system cools, oxygen grabs the available silicon and magnesium and locks them into silicate minerals. Rock, in other words. That's why the ground under your feet is silicate, oxygen 1. Almost all the carbon is left over as gas and gets blown out to the cold outer system, where it ends up in comets and the atmospheres of giants. Now flip the ratio, put more carbon in than oxygen, and oxygen runs out first. It gets used up, locking away the silicon, and there is nothing left to bond with all the remaining carbon. So the carbon has to become part of the rock itself. You build a planet not out of silicates, but out of carbides and pure carbon. And carbon, put under the pressure inside a planet, does something familiar. It becomes diamond. This is the same thing that happens beneath our own feet, just on a scale we can't reach. Carbon squeezed hard enough and long enough rearranges into the hardest natural substance we know. On Earth, that takes 150 kilometres of depth and 1 billion years of patience, and we dig frantically for the results. On a carbon planet, it wouldn't be rare at all. It would be the crust, it would be the mantle, it would just be what the ground is. So in 2012, a team took the star's carbon-rich reading, ran it through models of how such a world would build itself, and published the result: an iron core, above it, a thick layer of carbon, graphite near the surface, compressed into diamond further down, possibly a third of the planet's entire mass. Given the size of 55 Cancri E, that's a quantity of diamond it is genuinely difficult to write down. And that was the moment the story left the journals and became famous, because the number is irresistible. Put a market price on a planet's worth of diamond, and you get a figure with more zeros than the global economy. The kind of number that stops being money and starts being a joke. It's a wonderful story. It lasted about a year. The thing about that entire diamond conclusion is that it rested on a single measurement, made not on the planet, but on the star. And measuring the chemistry of a star is subtler than it sounds. You spread its light into a spectrum and look for the dark lines where specific elements have absorbed it. Each element leaves its own signature at its own wavelength, like a barcode. The trouble is that oxygen is genuinely awkward to read this way. Its useful lines are few and they're faint, and worse, some of them sit almost exactly on top of lines belonging to other elements. If you don't correctly account for the interloper, you'll mistake somebody else's signal for oxygen's or miss oxygen that's really there. In 2013, a graduate student at the University of Arizona named Johanna Teske went back to the original data and did something quietly devastating. She didn't take new observations. She just measured more carefully. Her team pulled the oxygen abundance from several different lines instead of one, worked out how much of the contested signal actually belonged to nickel, and averaged everything together into a fuller picture. The star was not carbon-rich. The reanalysis found the opposite of the original claim. 55 Cancri contains roughly 25% more oxygen than carbon. That put it somewhere between the Sun and the earlier figure, a perfectly unremarkable star, with plenty of oxygen to go around. And with that, the foundation under the diamond gave way. Not because anyone had looked inside the planet, nobody had, and nobody has, but because the one piece of evidence suggesting it should be carbon-rich had turned out to be a measurement error. Later work went further. The stellar ratio was revised again, and by 2016, a new model of the planet's interior had it as an iron core wrapped in a silicate mantle, which is to say, built like Earth, ordinary rock. 14 years on, that's where the science sits. The diamond isn't formally impossible. A planet's recipe can differ from its stars, depending on exactly where in the disk it formed, but the reason we believed in it is gone. The most precious planet ever found had turned into a fairly average lump of rock, which should have been the end of it. It wasn't, because there was a second number nobody had explained, and that number had nothing to do with what the planet was made of. It had to do with how close it was. 55 Cancri E goes around its star once every 17 hours and 40 minutes. Read that again, because it takes a moment to land, not 17 days, 17 hours. A year on this world is shorter than a working day plus a night's sleep. If you were born there, you would have a birthday before dinner and another one before breakfast. Mercury, the innermost planet of our own system and the one we think of as unbearably close to the Sun, takes 88 days. This planet does it roughly 120 times faster. To orbit that quickly, it has to be pressed almost against the star, around 1/50th of the distance from Earth to the Sun, close enough that the star doesn't look like a star from there. It fills the sky. And a world held that close doesn't just get warm. Its dayside sits at something like 2000 Kelvin, well over 1700 degrees Celsius. that is past the melting point of rock. So whatever this planet is built from, the surface of it is not solid. The dayside is an ocean of magma, molten silicate stretching from horizon to horizon, glowing, churning, with no shore anywhere on it. And because a world that close is almost certainly locked with one face permanently toward its star, that ocean never gets a night. It has been molten in the same place, facing the same fire, for longer than the Earth has existed, which raises the obvious problem, and it's the one that turns this story around. A planet in that position should be naked, because anything close enough to melt rock is close enough to strip a planet's air away entirely. The radiation heats the upper atmosphere until it simply boils off into space. Over billions of years, the star should have taken every last molecule. Any original atmosphere 55 Cancri E was born with is long gone, nobody disputes that. So when the most powerful telescope ever built finally turned toward this world, the expectation was simple. There would be nothing there, a bare, molten rock, blazing in the dark. That is not what came back. In 2024, a team led by Renyu Hu at NASA's Jet Propulsion Laboratory published observations of 55 Cancri E taken with the James Webb Space Telescope, measuring the planet's own heat across a range of infrared wavelengths and comparing it against every model of what a stripped, bare lava world should look like. The first thing they found was a temperature that was wrong. On an airless world, the dayside heat has nowhere to go. There's no atmosphere to carry it around, so the star-facing side runs blisteringly hot, and the far side stays comparatively cold. That contrast is a fingerprint, and it's what everyone expected to see. Instead, the dayside came back cooler than a bare rock should be. Something was moving heat away from its spreading energy around the planet, the way wind and weather spread it around ours. The second thing was more specific. There is a way for a molten world to fake an atmosphere. If you heat rock enough, the rock itself vaporizes, and the planet ends up wrapped in a thin haze of its own evaporated crust. Silicate vapor, not really air, just rock that has given up being solid. The team tested that model directly against the data. It didn't fit. The observations ruled it out. What the measurements pointed to instead was a real atmosphere, a genuine envelope of volatile gases, most likely rich in carbon monoxide or carbon dioxide. Actual air on a planet that should have lost every molecule it ever had. And that leaves one question standing, which is where this stops being about chemistry and starts being about something stranger. If the star tore its atmosphere away billions of years ago, and the star is still there, still tearing, where did this one come from? The explanation the team proposed is that the planet is making it. Not once in the past, continuously, right now. Think about what a magma ocean actually is. Not a lake of fire, a vast body of molten rock, and dissolved inside it, gases. Carbon, hydrogen, and other volatiles held in solution by pressure, exactly the way carbon dioxide is held inside a sealed bottle of sparkling water. Open the bottle, and the pressure drops, and the gas comes out of the liquid. That is not a metaphor here, that is the mechanism. Across the whole star-facing hemisphere of this world, gas is escaping from the molten surface into the sky above it. The star strips the atmosphere from the top, the magma ocean replaces it from below. That is the picture that emerged from the 2024 data. Not a dead rock with a leftover haze, but a world in a continuous exchange with itself, exhaling gas out of its own molten body as fast as its star can tear it away. The atmosphere isn't a survivor of the planet's birth. It's being produced, now, by the planet's own liquid interior. There's a word for a thing that loses its air and makes more of it, over and over, without stopping. It's not a word we usually get to apply to a planet. And here is what that does to the diamond story. We went looking for a world made of treasure and found instead a world doing something we had no expectation of finding, venting its own atmosphere into space, replacing it from a global ocean of magma, holding onto a layer of air by continuously manufacturing it against a star determined to take it away. Diamond is just compressed carbon. It sits there. It does nothing. This planet is doing something, which would be a fine place to end. Except the atmosphere won't hold still either. The strangest thing about 55 Cancri E isn't any single measurement. It's that the measurements disagree with each other. Look at this planet once, and then look again, and you don't get the same answer. Its brightness changes. Astronomers have known this for over a decade, since well before Webb, going back through years of observations that simply refused to line up. The planet appears to shift between one observation and the next, in ways that a stable, unchanging world has no business doing. More recent work has watched it eclipse behind its star 5 separate times and found the visits differing from one another. And the newest analysis have turned up something else strange in the mix. Alongside the carbon monoxide, hints of far more hydrogen than anyone expected, which, if it holds, would point to a magma ocean chemically different from the one in the standard picture. I want to be careful here, because this is the live edge of the science rather than settled ground. That hydrogen result comes from a very recent reanalysis that has not yet completed peer review. It may hold up, it may not, but the flickering itself is not in doubt, and nobody can currently explain it. The proposals on the table are all genuinely extraordinary, and each one implies a different world. Perhaps it's volcanism, enormous eruptions, venting plumes of gas that thicken the atmosphere and then fade. Perhaps the outgassing throws up clouds that briefly shade the surface, cooling it until the same outgassing disperses them again. Perhaps the planet's atmosphere is not permanent at all, but transient building up, escaping and rebuilding in cycles. Perhaps what we're seeing isn't the planet's surface at all, but a ring of dust surrounding it, shed by the world and drifting in its orbit. Perhaps it's the star doing something to the planet. We don't know. 14 years after we announced it was made of diamond, we cannot reliably say what its atmosphere is, whether that atmosphere is stable, or why it looks different every time we check. The one thing we can say is that it changes. Something on that world, or around it, is actively happening on a timescale short enough that we can watch it happen from 41 light years away. And this is where a distant lava world stops being a curiosity and starts being important to anyone standing on a planet. Because the question 55 Cancri E is answering, badly and slowly and with a great deal of argument, is one of the biggest in astronomy. Can a small rocky world keep an atmosphere? That question decides almost everything else. A rocky planet without air is a dead rock. A rocky planet that can hold on to air is a candidate for weather, for oceans, for chemistry, for everything we care about. And most of the rocky planets we're finding around other stars sit far closer to their suns than Earth does to ours, bathed in radiation that should strip them bare. If close-in rocky worlds are all naked, the search narrows dramatically. If they can somehow hold or rebuild an atmosphere, it widens again. 55 Cancri E is the most extreme test case we have. It is the hardest possible version of the question, the worst conditions, the fiercest stripping, the least likely place for air to survive. And the current evidence says something is there anyway. That's why so much of the most valuable telescope time in the world keeps getting pointed at a planet that isn't habitable and never will be. Nobody is looking for life there. They're looking for the rules. And it's worth sitting with how we got here. The diamond was never in the data. It was an inference drawn from a measurement of a star that turned out to be slightly wrong, and it went around the world before anybody rechecked it. Then a graduate student rechecked it. That correction is not a failure of science. It's the entire mechanism working exactly as intended, in public, on a famous result, in under a year. So, the diamond planet. It is almost certainly not made of diamond. The measurement that suggested it was has been corrected, the models have been rewritten, and the world that emerged from the rewrite is a rocky planet with an iron core. built along much the same lines as the one you're standing on, but it orbits its star in 17 hours. Its dayside is an ocean of molten rock that has never once cooled. It should have been stripped bare billions of years ago, and it hasn't been because as fast as its star tears the air away, the planet appears to be breathing more of it out of its own magma. And every time we look at it, we see something slightly different, and no one can yet tell us why. We went looking for treasure, and treasure is a static thing. A diamond is carbon that stopped moving. What we found instead was a world that never stops moving at all, losing itself and remaking itself over and over. 41 light years away, tonight, while you're watching this. The most valuable planet ever discovered turned out to be worth nothing and far more interesting. Thanks for watching, and I'll see you in the next one.